In class, I showed you how to calculate the electric potential due to discrete charges, and in the following recording you can see how we calculate the electric potential due to continuous objects. We will consider two examples, uniformly charged ring and a uniformly charged disk. We will begin with the uniformly charged ring having a radius r, and we will ask the question of the electric potential due to that ring at the distance x along its symmetrical axis. We can consider individual small parts of the ring that will create electric potential, and each of those points along the ring will be at a distance square root of x squared plus r squared from that point where we need to calculate the electric potential. Then we can use the formula for the electric potential due to a point charge, which is k dq over r, and here dq will be the charge of an infinitely small part along the ring, and the distance from that point charge to the location where we want to calculate the electric potential is square root of x squared plus r squared. The next step is to integrate, and we'll have to integrate over the ring, and that's why the circular integral symbol here. Once we write that the potential due to each individual point along the ring is equal to k dq over x square root of x squared plus r squared, we notice that there's only one variable under the integral, and that's dq. So simply we will integrate over that dq, and after we are done, the result will be the total charge of the ring Q. We can highlight this is the result for the electric potential created by a uniformly charged ring with a radius r at the distance x from its center along the symmetrical axis. Here we can actually ask an interesting question. Can you derive the electric field due to a ring using the formula, the highlighted formula above? We already derived that expression from basic principles, but here I would like to show you how you can get to that result by using the result for the electric potential. First, we know that the electric field points along the x only. In other words, you can have only x component and no y or z, due to the cylindrical symmetry of that ring. And so there'll be only one component, x, of that electric field, and that x component will be equal to minus the derivative of the electric potential with respect to x. The rest, we just need to differentiate the expression that we obtained for the electric potential and calculate what is minus d dx of kq over square root of x squared plus r squared. I'll leave it to you to work out the details. I will just write the final result. After the differentiation, everybody should get the following result: k, q, the total charge of the ring, x, the distance from the center, over x squared plus r squared to the power of 3/2. The second example is how to calculate the electric potential due to a uniformly charged disk with a radius r, again at the distance x from the center of that disk. We will use the result for the ring, and so I will write here the result for the electric potential due to a ring with a radius little r is equal to k dq, the charge of the ring, over square root of x squared plus r squared. Here r is the radius of the ring. I switch it to a little r since big R here will stand for the radius of the disk. Little r is the radius of those little individual rings that we will consider, and each point along those rings will be at a distance square root of x squared plus r squared from the point where we need to calculate the electric potential. Remember, the disk is uniformly charged, and the surface charge density then defined as the charge per unit area is going to be also equal to the total charge over the total area. Replacing the area of the ring with 2 pi r dr. And if you don't remember the area of a ring, I recommend that you go back and review the recording on the electric field due to a disk, and there all the details are given. And also we're going to replace the area of the disk with pi r squared in that ratio for the surface charge density, and get the following expression for the charge residing on that ring with the radius little r. It's going to be equal to the total charge over the radius of the disk squared times 2 r dr. With that, we are ready to integrate. We write the integral for the electric potential due to the entire disk as integral over k 2q over r squared times little r dr over square root of x squared plus r squared. Here I have used the result for the electric potential due to a ring, and I have replaced the charge residing on the ring with the result that we just derived. The limits are from the smallest possible ring that corresponds to radius little r equal to 0 to the largest ring that we can see on the disk, corresponding to a ring with a radius equal to big R, the radius of the disk. The integral is going to be solved through substitution. We replace x squared plus r squared with the new variable z, and quickly we can see that 2r dr is actually equal to dz, and the new limits, we can figure out the new limits by looking at the little r, which is our original variable, as it goes from 0 to big R, the radius of the disk. The new variable z will actually go from values x squared to x squared plus r squared. With that new variable, our integral for the electric potential becomes integral from 0 to r k times 2q over r squared dz over 2 times square root of z. The integral is very simple. What comes out of the integral is simply a square root of z. And here the limits for the new variable are x squared and x squared plus r squared. What is remaining is to evaluate at those limits and write the result for the electric potential due to a uniformly charged disk as k times 2q, the total charge, over the radius of the disk squared, times the expression in the parenthesis, which comes from the integration, square root of the radius of the disk squared plus x squared minus the square root of the distance squared. Here I have left the x squared under the square root simply because otherwise I will have to worry about the absolute value and whether x is positive or negative. And that is the result for the electric potential due to a uniformly charged disk. Once again, we can ask the question, well, what about the electric field of that disk? Can we calculate the electric field due to such a disk using the result for the electric potential? And of course the answer is yes. Once again, we have the cylindrical symmetry, so the electric field has only x components, and that x component will come as the minus the derivative of the electric potential with respect to x. In other words, you will have to calculate the minus d dx of the highlighted expression above. I will leave it to you again to work out the details, but the final result should be minus k times 2q over r, the radius of the disk squared, multiplying the following expression, x over square root of r squared plus x squared minus 1. You can compare that expression with our result that we obtained for the electric field due to a disk, and it should look identical. If it doesn't, let me know and we can see I can answer any questions in class.